Okay, for our last flash talk, we have Sridhar Sundaram, founder Maza Learn, talking on leveraging scale to improve human learning.
Okay, I am going to talk about leveraging scale to improve human learning. So, a brief introduction about myself. Right now, I have a company called Maza Learn, which is basically to have fun while learning. Before that, I was at Google, where we are working on monetizing ads and speeding up the web. In California, I was working on monetizing ads. Later, I shifted to India, where we are working on how to speed up the web to sub 100 millisecond web pages. Before that, I was in Lotus Interworks, and before that, I was in my own startup called Mind's Eye. So I have a BTech from IIT Delhi and a PhD at Cornell. So this realization hit me while I was at Google when I read this article, which basically said all smart people are sitting in these .com companies trying to figure out how to make people click on ads. I realized that that's not what I wanted to do with my own life. So that's when this whole quest started. Can I do something better with my life? And this is where I am now. Okay. So what is education? This is what Einstein has said, that it is what remains after one has forgotten everything one learned in school. And in my life, I found that to be substantially true. I hardly remember anything of what I've learned. And this Angry Birds motif is there because that was one of the motivations for me to start this whole sequence of actions towards learning. What I found was when my kid was about 8 years old, he used to love this game, Angry Birds. And I used to tell him, read your science book. And the comparison is meaningless because a science book is this boring, old-fashioned thing which you turn around, there are words on the page. And Angry Birds is this exciting, colorful thing. You do things like this and it moves. So I thought we have to do something about this, and that's when this quest started. So Maza Learn was founded at that time. I also believe that education is fast reaching an inflection point. Inflection point is a point at which things dramatically change. So the last time this happened was when Gutenberg founded the printing press, when books got printed. Before that, we had this Guru Shishya, where the Guru used to sit and advise his children how to behave in life, what to learn, how to learn. Then this printing press got printed, and suddenly schools became like an industrial product, where the kids are the raw materials, they come in, the teachers mold them one after the other in the different classes, and out comes the school student who has passed. And if we are lucky, the school student might be able to recite Newton's laws extremely well. For the first time, we have an opportunity to change that today. We have this internet, tablets, and massive online open courses all converging together into a movement. But in learning and education, things change slowly. Part of the reason is we don't want to risk the lives of our children over some experiments that we would like to do. It's almost like this doctor who said to his mechanic said, how come you are paid so much? I also change the wheels of the car, I also tune the engine, and you tune the patients. How come you are paying so much more for you? And he said, try tuning your car while it is running at 60 miles per hour. So education falls into that category where we don't want to take risks because they are live children, they are our future assets who are going to live. That's why education changes slowly. But I still believe that within the next 5 to 10 years, things will dramatically change. That our children will be able to use these things, these tablets, touch, internet, and suddenly be able to be dramatically better at learning. There are some educationists who believe that children are learning at 1/10 the capacity they could learn. And there are others who have said that before the age of 2, any human being has learned 99% of what he's going to learn in his entire life. Think about that. Before the age of 2, they have learned almost everything they need to learn. This is a prediction by IBM made in December 2013. That it's not just that we are learning, the classroom will learn you. What they mean by that is the classroom will adapt to the learner. It will change the way things are taught so that the learner can learn more efficiently. And this is the direction in which we are going. Long ago when I was in, I think, 8th or 9th, I asked my teacher what a wave was. And she said, a wave is an excitation which travels outward at a constant velocity. And I understood nothing. And then this other teacher said, imagine you're standing in a supermarket queue and I push you from behind. You don't move forward, but what I did, that push traveled all the way forward. That is a wave. So I understood at that time what a wave was. And that is a similar problem where the learner's perspective has to be kept in mind when we try to teach something. And that is what this prediction means, that the classroom will learn you, that the classroom will change its contours to fit the learner. So we come to the topic of this talk. How can we use scale to improve learning? By scale, I mean data from a large number of learners. Can that be used? And learning, by learning I don't mean the memory-based, rote-based learning that we see in schools. I mean learning which is conceptual, deep and rich, where things are not forgotten as soon as the class is over. So I'm trying to categorize levels of intelligence at scale. This goes back to how Lord Kelvin said this. When I talk to teachers, they say, yes, schools should improve, teachers should improve, books should improve, but there's no quantitativeness in that statement. Unless we can quantify it, unless we can measure it, it's very difficult to improve things. So this hierarchy is an attempt to qualify or quantify what we are talking about. What do we mean by intelligence at scale to improve learning? So at the bottom level, I will go through examples of this. I have tried to relate it to Flipkart so you can identify that more easily. At the bottom level, I call it as inventory tracking, which is like a standard Flipkart product, which is a black box which is shipped to the customer. At level 2, I call it as time tracking, which would be the case with e-books, where you can actually read it using a Flipkart book reader or something, which tracks the amount of time spent on each page. At the third level, we don't yet have it, but it would be an e-book which also assesses, which figures out whether you understood what you read or you just read it. And at the fourth level is something which I'll have to demonstrate to you. It is adaptive in the sense it changes the content based on your learning capability. So let's go a little deeper into these 4 levels. This is an example which I'll use throughout. This is like the physics Cambridge IGCSE course book, which is sold on Flipkart. And suppose we could track inventory, that is level 1. What would we see? So we'll see quarterly sales by region or some such similar summary. For some reason, the East region is not doing well. Maybe people in East don't like physics, or students in East do not go for science. We don't know what the reason is. So this is the sort of intelligence we can glean from this data, that something is wrong with the East region, which is good. Can we do better than this? So now we do time tracking. By time tracking, I mean that we can actually look at which topic or chapter people who are reading that book are spending time on. So here there are 4 topics. I hope you can read them. There is bar magnets, induction, fields and motors. And you can see that induction is where people are spending time. Now does that mean they didn't understand induction? Did they love induction so much that they read it again and again? Or they didn't understand induction and they read it again and again? We don't know that. So we need a little more depth. So move on to an assessment-based tracking system. Assessment reminds me of this teacher in school who used to keep asking us after explaining anything, do you understand? This is what this is, understand. And so very soon we started calling her misunderstanding. So that we don't have a misunderstanding, we want to figure out whether that person who is reading actually understood or not. And this understanding can be measured either implicitly or explicitly. We'll figure out both methods later when we go to the demo stage. But assume for a moment that we have figured it out. You can see that the success percent on induction is very low. Most of all the other 3 are above 80%. Induction is less than 50%. So there is something wrong with induction. So that is the extent to which we can figure out what's happening if you look at tracking with assessment or learning aware systems. Finally, we move to level 4, which I would call as adaptive systems. And we take a page from the book. This is page 229 from the same book that we saw earlier. It talks about electromagnetic induction and how you can do an experiment. And then below it starts writing the laws of induction. So here's an attempt to do it better. So here we basically have a bar magnet, a bulb and a meter. And if we move the bar magnet, it lights up. If we increase the number of loops in the coil, there is more light. If we reduce the magnet strength, there is less light. So this is the sort of thing we are trying to do. We are trying to drive that white box abstraction so deeply into the mind that there is nothing to remember anymore. You basically understand it. That is comprehension at the conceptual level, not at the memory level. So this whole application which we have is available on Android and iPhone both, because we want to target both audiences. It basically tries to teach science as a white box model in terms of active experiments. By white box, I mean you can actually see things which are not there in nature. So if I take this example of a bar magnet, you'll see what I mean. So you can actually see the field of the bar magnet. You won't actually see it in real life, but here you can actually see the arrows showing the strength and the direction of the field. So it's a white box model. The intent is that the child should be able to play with it, hopefully like Angry Birds, and understand what's happening. So now let me go back and try to come back to this idea of what we are trying to do. So basically the emphasis is on doing, because involvement automatically generates comprehension. So this is a pyramid called Dale's pyramid. It is not actually quantitatively accurate. Those percentage numbers are estimates made by this person called Dale, which are not actually experimentally observed. They are just his estimates. But it is very close to truth in our experience. When you do a dramatic experience or simulate the real experience, 90% is retained. When you read it or hear it, like in this talk, only 10% is retained. So if we were giving this talk, you would ultimately retain most of it. It is like saying Sachin Tendulkar plays very well, but if you have faced Wasim Akram and then seen Sachin Tendulkar play, you will see the difference. So this goes back to the idea that I hear, I forget, I see, I remember, I do, I understand, as stated by Confucius thousands of years ago. So this is what we are trying to do. We are trying to make sure that the emphasis on doing, is on understanding, is on really comprehending. And we came up with this idea of debugging human learning. Just as we have bugs in the software, there are bugs in human understanding. And all of us have these bugs. We might not realize it. I had this bug about waves for a long time, for years. I used to think that in a wave, particles actually move, until I realized that they're only sitting and oscillating in one place. So how do we remove these bugs in human learning? For example, here are some other bugs we found in electromagnetism, that a magnetic field requires contact. The magnet has to touch for it to attract. The south pole is stronger than north pole. The bar magnet has to touch the coil for current to be induced. AC current just flips from positive to negative instantaneously, and then negative to positive instantaneously. So these are all observed when we actually looked at students. And what we would like to do is use intelligence at scale to identify, track, and correct these concept bugs. So now we are putting all these pieces together. We have this app distributed all over the world. Lots of people are using these apps. We are observing how they are spending time, where their comprehension is failing, where they are not able to understand, identifying those points, gathering them, trying to figure out how to feed back a different thing, so that when they use it next, they will actually be able to get over that hump in understanding. So to do that, we need a lot of infrastructure. This infrastructure I have summarized into 4 layers. There is a connectivity infrastructure. There is a knowledge markup, where we need to split up knowledge into little pieces so that we can figure out which piece that person is not able to understand or is able to understand. The assessment piece, which tries to figure out whether that person has understood or has not understood or what is the problem. And there is an adaptive feedback piece, where this information goes back to the learner to try to get him over this hump in understanding. Let me go a little bit deeper into each piece. This is the simplest piece conceptually, where there are learners and there is a server and there are instructors and they're all connected over the internet. And actually it is the most important piece technically, because what they say is, when you're doing a tough project, you should have your best person on the other side. In this case, the best person on the other side, that is the device side, happens to be your infrastructure. If your infrastructure fails, everything goes wrong. It doesn't matter how well you have written the server code. So we actually had a bug in this infrastructure piece for some time, where the information was not flowing back, and for 15 days we were stuck. So infrastructure is where we connect all the pieces together. Data is flowing back and forth from the device to our server, from the server back to the device. Right now, as a sidebar, we are hosting it on Google App Engine on the server, and the iOS and Android devices are on the learner and instructor side. And these devices are periodically syncing with the server using HTTP. So that is the device side. On top of the device, we have this app which understands knowledge in little chunks, which we are calling as knowledge units. Every chapter consists of a large number of knowledge units. Each knowledge unit is like an atom. It cannot be split further, at least for this app. It understands that this person understood this unit or didn't understand this unit, and that's about it. So here's the flow for a knowledge unit. The learner starts on the knowledge unit. There's a series of events he's trying to understand. For example, he's trying to move the magnet inside the coil. He's trying to understand. At some point he understood, or he did not understand. So there is success or failure. And all of these events are getting tracked, the transitions and the events. And these events which are tracked are sent back to the server from the device. So that is our knowledge markup. Assessment. So I talked to you about misunderstanding. So assessment can either be explicit like that, where the app keeps popping up. Did you understand this? Did you understand this? Which is a bad way of doing it. But it's possible to do that. In some cases, it actually becomes necessary. So for example, in this first version of this app, my son is in 10th grade. He said, he did all this app. Then he said, I don't feel satisfied. I asked him why. He said, there are no questions at the end. So that the students have been trained in such a way that we need to give them this explicit notion of progress for their own good. So explicit assessment has to be there. That's why we later added this multiple choice questions also. In other places, I've seen something called echo back, where the teacher writes on the board. We actually studied how teachers teach in India. Went to a school and the teacher writes on the board and the students read it out. And then the teacher writes another line, the students read it out. So that is the echo back model of assessment. And we have implicit assessment, where there's an event stream. We are capturing everything that the user is doing. Click here, touch here, moving this thing there, moving this thing here. That event stream is sent back to the server. The time spent on each knowledge unit, that is sent back to the server. And what we try to do is we make challenges or games which exercise these knowledge units. I didn't actually show you a game. I'll show it to you later. So basically, there are rules which are sitting on top of a rule engine. So there is a simulation engine. On top of it, there's a rules engine which enforces the rules of the game. And basically, the games are trying to exercise knowledge. They're trying to figure out if this user understands this fact or not. So all this information is being collected. Based on all this information that we have collected, we are sending adaptive feedback. Now, adaptive feedback part, it can either be collective, that is all students in grade 8 who are doing electromagnetic induction or getting stuck in moving the magnet, or it can be individualized. This person is getting stuck when he does this particular exercise. And this individualized feedback can use existing knowledge about that specific learner. That is going back to the idea of learning about the learner, the classroom learning the student. For example, if we realize that this person is getting stuck in the magnet thing, we can pop up hints. Does the magnet have to touch the coil for current to be induced? Or we can say, do you want to revise this particular topic? Or we know that this particular learner already understands this but doesn't understand this. So we change the path for him. So instead of showing bar magnet and then the magnetic field, we show magnetic field first and then show the bar magnet. So those are all individualized adaptations. Then we can have collective adaptations, and I'll show you one example very soon. Collective adaptations where we realize that a whole category of people are getting stuck somewhere and we need to get them over this hump of learning. So there we have to show some very generic idea, and this cannot be automated in my opinion. So let me go to this example. So here what we found was there were some people who took this magnet and they used to take this coil and they kept moving it. They kept moving it. This is not like we observed in many instances from the event streams that they kept doing this. They wouldn't stop and we couldn't understand why. So this was not like 30 seconds. They used to do it for 5 minutes. We were completely flabbergasted. Then we went to a school and we actually distributed some tablets and asked the kids to do it, and they did the same thing. So we asked them and they couldn't explain. And then we realized that when we are exposed to some new phenomena, it often takes our mind time to understand and absorb that phenomenon. And we are not giving enough clues to understand it. So then we added this graph at the bottom that you see here. You'll see the graph momentarily. When I move it, the graph moves up and down, showing the current being induced. And if I rotate it, for instance, also, there's a current induction graph. This release has not yet gone out. We are hoping that this will solve this problem where people are getting stuck in trying to understand what is happening in this case. So this is one example of adaptation which we don't think we can automate. The other examples we can automate. The hints are simple to automate, right?
Here, this is what you are capturing was people spending a lot of time on this particular thing.
We capture the event stream. So this was the graph example, and we don't know whether it will work. We believe it should solve the problem where they want to get insight into this process of magnetic induction. We're also thinking that maybe we have to show the formula for magnetic induction, show them in pieces like magnetic strength increases or number of coils increases, something like that. We'll have to experiment and find out. So that is the adaptive feedback part. So some statistics on what we have done so far. We launched this, I should show you an example of the game because we're calling it science game. It's unfair to not show you a game. So here's one example of a game which we are calling as Motor Monkey. The idea is that you have to make the monkey climb up by using the principles of a DC motor. And after writing this game, I understand DC motor extremely well. So basically you need a commutator, and then you need to tune the current appropriately and then give it a starting flip, and it will go up. So I explained it in a very simple way, but when you do it, it's much harder. So this is the idea, that the game is exercising knowledge of atomic units of comprehension. So we have a game at every level like this, which are simple games, and I will come back to learning about it later. So we launched in December on Android plus iOS. We have only done electromagnetism because we found that that was a hard topic for children because there's nothing to hold on to. In mechanics, they understand that when you push something, it moves. There is friction. All these things they understand from when they were a child. Electromagnetism, there's something new. It's not clear. So even today, they don't understand how a fan works. So we asked in the school how fan works and they didn't know. They said, I switch it on and it works. But they didn't understand that basically there's a motor and there's a coil. So that's why we tackled electromagnetism first. And these are two other topics we are planning to target, waves and states of matter, which will probably be end of April. And we are getting about 100 installs per day. We have done no marketing, so 100 installs is pretty good. We will do the marketing only after we are confident that we actually solved the problem, because our intent is to, as I said, I started with ads monetization as a background. So my intent is not to earn money from this, but to make things happen. And so far we have got about 10,000 installs, and we are still observing how people use it. So what did we learn from all this? The first thing is the user interface is extremely important for a consumer-facing app. So when we launched our prototype version, we saw this, that all the feedback we got was about the user interface. This box is big, this font is not big, this thing is not clear, that is not clear. So we spent almost 4 months cleaning up this user interface. As soon as we cleaned it up, we went to the next level, where they're sorting out the real bugs in the application now. They still hadn't reached learning. So they pointed out that when the magnet touched the corner, it bounced back. They pointed out that when the magnet was not spinning properly. So we fixed all those problems. Then they finally reached the learning problems, where they started really getting trouble with understanding concepts. So what it shows is you have to get your pieces in the right order. Before you can solve a problem, all the infrastructure has to be right. So for example, here was this example which I gave you about the bar magnetic induction. The other example we saw was where they're trying to move the compass. I think I'll skip that. So it's complicated. So basically that's one important learning, that learning happens only if everything else has already been solved. So when we look at our science books today and we say it is not good, we are ignoring a lot of work that has gone into it over years, where the science teachers have figured out what pieces to put in, what pieces to leave out, in what order to approach the topics, and still we are only at a particular stage in evolution. So when we try to do the same thing using an application, we should take all those learnings into account and put them in. And it has to work. It cannot be that there are bugs in it and we expect people to learn. And there's one other piece I wanted to tell you. Yeah, the other piece I was telling you was, I don't think scale can automatically solve all problems. Scale will definitely detect some problems, and then we have to solve the problem on our own. So this is like saying that there was this argument we had at Google, where one very new engineer was doing some MapReduce stuff, and he said, and we asked him, okay, how are you doing? He said, well, I ran this MapReduce on 0.001% of the traffic. For Google, 0.001% of traffic is very large, but I'm not getting any insights. Tomorrow I'll run it on 1% of the traffic with MapReduce and I think I'll understand it. So unfortunately, scale doesn't solve the problem. You have to have some hypothesis, you have to have some ideas about what is the problem, and then scale can confirm that diagnosis. So this part I don't think can ever automate. That is why I had shown you this picture in the infrastructure, where there are instructors also in this system. I think the instructors are the people who will actually understand what the problem is. What we can do is surface problems, like too much time spent, comprehension not enough, and show the points at which scale has identified these problems. Scale will definitely help us identify problems, but debugging and solving the problems, I think we'll have to have human instructors available. To some extent, scale will help. Once we have identified and solved a type of problem, we might put pattern matching in place on scale and try to solve the same problem in other places. But it will not automatically solve the problem. Okay, so yeah, that is all. Basically, this is how we are trying to leverage scale to improve learning. Any questions?
So I'm playing the devil's advocate, but I'm curious about your reaction. So I'm just curious about your reaction, right? So I mean, one could argue that by putting all of these pictures and animation, in some sense you are spoon feeding to the kids, so they never really acquire the habit of thinking and learning, right?
No, it's a thought which passed through our mind. But here's the problem. We are giving them this Angry Birds kind of games on one side, and we are giving them the school science textbooks. There is no comparison. You can say it's spoon feeding, but if you don't do that, they are going to play Angry Birds instead. And the second thing is, if you play these games, the graphics and all may be very good, but it's not so obvious what to do to solve the problem. So in the review pages in our app, there is one person who has written, impossible, I cannot solve this. So it shows that the concepts, if you don't understand, you cannot solve them. They might look good. And that is actually the problem. I was talking with Himanshu. Himanshu was the person who invited me here. He's here now. So the basic problem we are seeing is kids like to act. They like to move magnets within coils. But as soon as we force them to think, they dislike it. So, because learning is a hard process. It's like mountain climbing. So we need to figure out a way to make learning attractive. And what I think we have learned is that we cannot substitute the recreation time with this kind of application. It has to be the education time which has to be substituted. So if we try to tell them, okay, don't play Angry Birds today you'll spend it on this science game, I think it will not work. This is the conclusion we are coming to. But instead, if we say, instead of spending half an hour on your science book, spend half an hour on science game, they'll be very happy. And they will probably learn more.
The scope of peer-to-peer learning in this, for example, group studies, in the offline world, group studies works for some students and doesn't. But in recent research, maybe about 10 years ago, there was a book called The Gamer Generation, where two researchers from Harvard, they noticed that kids were not learning from their parents, but as an impact of the Nintendos and the Ataris, they were learning and teaching each other, and there was a lot of peer-to-peer learning. Is there scope for the app to kind of will it have scope, say, on a social network where you can have the equivalent of group studies?
I think absolutely. I think that scope will definitely be there, but let me step back and give some more perspective. There is some research at Harvard by Professor Mazur, and what he found, this was a graduate class, not at the child level. Child level I understand completely. I have seen that peer learning is more dominant than school learning. But even at Harvard undergrad classes, where they allowed collaborative learning, in the sense the professor would write something on the board and then ask the students to break up into groups of 3 and discuss it, and then ask them the same question, which ones they agreed it and which ones they didn't agree with. He found that learning had improved by about 50%. So definitely collaborative learning is better, but we don't yet know how to systematically produce this kind of learning. So it will have to be an experimental affair for some time. Once we figure out what exactly works, it will come, but we are still some years away from it. So right now we are still struggling with the very basics, which is how to make a child want to learn. That is, today the way we teach science, if you go through this Kannada Karnataka board science book, it is worse than my history lesson. It says a DC motor has 7 parts. It has got a commutator, it has got a magnet, it has got a coil. Obviously, no child is going to like that. So we are still struggling with the very basics. Collaborative learning will be important, but it will come once we have solved this very, very basic problems.
How are you measuring the effectiveness of this? You said that while you're not worried about the installs right now, you really want to solve the problem.
Yes.
So I think it's great the way you are leveraging scale or getting data symptoms. So how are you actually learning that it is being effective?
Only
Success metrics to actually improve the product.
only way is look at the event streams. That's the most reliable.
Like you said, the event streams point to a problem. Ultimately, you're saying if the
Well,
event stream is getting solved, if you're
yeah.
addressing it and you see that event stream either going down or going up, whatever direction it's supposed to take, if it's taking based on your actions, you're saying that's the improvement.
Well, if the time spent somewhere is high, then we can suspect a problem. If the
Qualitative angle to ultimately, there is multiple choice questions, etc. But it's ultimately gamification. A lot of it could be by chance, and some of it could be real. So
the chance thing reminds me, before we did the science game, we actually did a maths game. And there we found that all the learning was by chance. There was no learning. So we gave up on maths for that reason. But in science, we found that by chance is much harder. You need to have a logical model of what works before solving those games. You might,
like you said, they keep moving the magnet. They could do a bunch of things, and the monkey goes up. But
yeah, so they'll be able to do it once, but there are multiple levels in it. And if they're able to do it more than once, then more power to them. They're very good. They will do as well in science also then.
I would be curious to actually see a multi-level kind of a thing that you made to have the learning, to demonstrate the actual learning happen. It would be nice to see a multi-level game kind of.
Multi-level game. Basically that same game, we remove some controls. For example, right now I think that game is showing you all the controls. I can't get to level 2 without crossing level 1. It will take some time. So in level 2, basically your magnet is no longer configurable. You have to do it only using current in the coil. And then at level 3, current in the coil can only be AC, it cannot be DC. So things like that will happen. Basically, we are constraining the path so that unless the child has actually learned that stuff, they cannot progress. But it's not perfect. There are a lot of problems with it, which is one reason we believe that long term it will be like a Wikipedia. We will create an infrastructure like this, and teachers will be able to put in their own little markups on top to exercise the knowledge units. But we are nowhere near that stage. We are still very early. It will take time.
Any specific reason you chose electromagnetic as any specific reason you chose the hard problem to be solved?
Because if we cannot solve the hard problem, then solving the easy problem doesn't help. We have to be able to solve at least one really good problem. And if we are able to solve it, we have hope that this approach works. Right now, we are not even sure this approach is good. So electromagnetism we chose because of the white box potential, and it is conceptually deep. While Newtonian mechanics is a good thing, but most children have intuitive appreciation of Newtonian mechanics. So we will not be able to figure out whether they learned because of the application or because they already had insights on their own. So here the source is much simpler. It's only our application. So we're going to do a trial with Canadian school. Because of this reason I mentioned that I don't think we can substitute the recreation time with science games. So we're going to do a trial with Canadian school where we try to substitute their education time with science games and see if they learn better that way. So by end of next month we'll know.
So we see a lot of problems that we're trying to address through this is more a specific medium-centered thing. What about the psychology-centric problems of learning?
Could you give some examples?
Okay, see for example, we are transitioning, let's say, from a human interface of teaching to, let's say, from books to, let's say, a particular medium like a tablet or a game or a computer, right? Okay. Now, that induces a bunch of challenges. I mean, when I'm reading, I don't know what it means to move a magnet. All it shows me a north-south pole and puts an arrow. I have to imagine.
Yes.
And then there I can't imagine the speed with which it is rotating, so will it make a difference to me in the intensity of current that gets generated, right?
Yeah.
So when I bring into a new medium like this, where, I do something and it starts to rotate fast, and then, somebody does it slow, somebody does it fast, so there is a clear result and I'm able to correlate that.
Okay.
That's one set of problems that the medium is introducing, and therefore we can address them elegantly.
Okay.
But what about a fundamental thing? Like, for example, I was very good at optics probably, but somehow there was an unknown fear of electricity for me. Kirchhoff's laws were Greek and Latin to me till the day I said, look, I need to solve this for myself. Okay. How do we address that through these things?
So unfortunately, I'm going to give a negative answer. I don't think we can address those kind of problems. The teacher is required. You're asking that whether a teacher can be substituted by this kind of application? I don't think so.
Sorry, even I am confused with my question, but what I was trying to see is, what is it that induces a uniform level of motivation to say that, yes, I want to learn this, I can solve this, I don't like it, but after a point in time, I'll leave it. It doesn't matter to me. Okay. But how do we get a child to get to that level of motivation to say that this is what I want to do? I mean, does this medium solve that problem? Or is there something more that can be infused or injected into the way we are structuring this whole thing so that at least we can mitigate to a certain extent?
So when we started about 2 years back, we had a lot of hopes in this direction. Then I spoke to one of my friends who is actually a professor here in IISc, he's in cognitive sciences. He said, learning will never be a game. So it is too much to hope that the child will willingly come to do learning because of this problem of having to think. Learning happens only when you think. There is no way of avoiding that. So we can bring, as they say, you can bring a horse to the water, but you cannot make it drink. You can bring a child to the tablet, but you cannot make him think. So we can bring the child to the tablet with all these attractive games, but if we want them to learn, that motivation has to be either internal or from a teacher who can inspire them. I don't think we are at a stage where we can inspire them using a tablet.
These kind of gamifications are good and everybody learns. It makes learning very easy actually if you can do things into the right direction. But will it not move a child away from the books? Like I can think like if I am getting something which I can learn easily this particular thing this way, then why will I read book?
I have a very strong reaction to this. It is like in the terms of long ago when Fortran language was being invented, people said, it's not good, we should write in assembly. The best programmers write in assembly. Why should you need this Fortran and Pascal and all these bad languages? So history has proven that that is not the right model. We do need all the crutches that are possible to aid in our understanding and conceptualization. And they always help us because they move us to a higher level. There are lots of problems in the world. We want them to spend all their time trying to read because they have reading problems. Do you know that most of the PISA, bad results in PISA are due to reading ability problems, not due to science ability problems. Indian kids are actually pretty good at thinking. But when they pose the question in a word problem, saying that this magnet moves at a velocity of this at this level, they are not able to understand it. So we are constraining their scientific thinking using reading ability. I think this will actually get over that problem, where they are no longer judging them by the reading ability, but by their scientific thinking ability. So we are decoupling the two. So I think it's a good thing.
So here, to the right side.
Okay.
So, give me your insights at like up to what level you can make these interactive games, and like 8th class level, up to 8th class level students will learn through this interaction mode.
Yeah, excellent question actually.
And then another question to follow up also.
Okay.
So like if you are making children use it to this kind of interactive learning kind of stuff, and we can't make it to the next level also. Like you can't make these interactive games to the advanced topics. I believe that like advanced topics you need to learn, like you read and you need to learn it. So if children are used to this kind of interactive learning, so will they, their ability to learn will reduce?
So let me go to the first question. So if you look at the iPad marketplace or even Android marketplace, most of the games are targeted at kindergarten and first and second and third graders only. So they teach numbers and alphabets and fractions and letters. And then if you look at the internet, if you search for science games on it, you'll find all undergrad level, engineering level. We haven't found many games targeting the secondary school stage. We are not sure yet why. So what we did was actually looked at some of these undergrad engineering sites. There is some good sites like PHET, Colorado State, Chicago. They've got good undergrad interactive, not games, undergrad interactive science simulations, and we copied some of those ideas and we constructed it for the 8th and 9th and 10th graders right now. So we are targeting them because I think they are at a stage where the novelty of the tablet is not the important thing. They really want to understand things. So that is from my own experience, because my son is about in 10th grade, and I realized that he is no longer worried about all this. He is not so much interested in Angry Birds anymore. He wants to understand things. So to that extent, I think we are in the right age bracket. As to your second part of the question, whether we'll spoil the kids, that again I have a very strong reaction to. I think when we teach our children to ride a bicycle, we hold that cycle and later we let them go. I think it's the same here. We are trying to teach them to think in an abstract way. We are trying to teach them the white box models of the world. We are trying to teach them what scientific thinking can do, and then we have to let them go. So at some point, they will transition from a world which is very nice and interactive to a world which is a little bit sparser, which is full of mathematics, and that's the best we can do. And if you have gone, I actually enrolled for a graduate course in quantum mechanics when I was in Cornell, and this was a physics course, but everything was mathematics. So I dropped out within a week because I couldn't, I couldn't handle the mathematics. So I don't think it is anything to do with interactivity which is spoiling your ability. I think at that level, when you are going into higher studies, it's about whatever is innate interest in that person will definitely dominate. But right now, what's happening is we are discouraging a lot of people with innate ability to go into science because we are not giving them sufficient support and power because we don't have good enough education system today.
So, if you look at content today, there is books, right? Then there will be video content and then there is interactive content. When I look at some of the things which you have shown, I genuinely believe video content would have served most of the purpose, and I don't know how much interactive content would have helped in this case. What is your viewpoint around that, and why do you think interactive content is better than just pure video content depicting what you had shown?
So this goes back to the Dale's pyramid that I showed you. When there is involvement, actually there is a dramatic improvement in the amount of absorption that we have. So there is an experiment which was done by a PhD student in Sydney. Can we turn on this projector? It's gone to screensaver. No, that one is on. So there was this experiment done by a grad student in Sydney where he had this very beautiful video of a professor explaining Newton's laws of motion. And there was another video which he made as an experiment where there were two students arguing about Newton's laws of motion. And they were making all kinds of wrong generalizations, bad generalizations, pitching wrong laws. And then he had a control group and data group, and he tried this experiment systematically, where one group was shown the nice professor's video, other group was shown the student arguing video. And mind that the student arguing video was actually technically not correct. But still the students learned more in the argument video because of the involvement. So basically the problem with videos is involvement is low. It becomes a passive mode of instruction where the concentration goes away after some time. So this child is watching the video, after 2 minutes he's thinking about his friend, then he's thinking about something else, and then he comes back to the video. So because of the lack of involvement, this problem comes. We can't tell because none of these marketplaces tell us the age groups. One thing we do know that the parents are involved because kids don't have access to downloads on their own. Usually, we are targeting 8th to 10th grade. But as I said, I think we are coming around to the conclusion that this cannot substitute recreation time. So the marketplaces may not be the right mode of distribution. I think the mode of distribution has to come through the schools. And the schools have to substitute their physics labs or physics lectures with this kind of instrumentation, and that is when it will be more successful.
Motivation to study aspect in the game. He pointed out, will the kids be motivated enough to do it? Have you tried incentive based, like say, we have been talking about Angry Birds. Could the kids get some credits on Angry Birds if they solve this monkey puzzle?
So actually, one of the co-founder actually wrote a version of Tetris, which is playing Tetris, and at a particular challenging time, it asks a question: what is 7 plus 13? Something like that. And if they answer it, the challenge goes away and the Tetris becomes much easier to play. So we don't know. We don't know the answer. At least in that experiment, we didn't find positive experience, but it's possible that. So in a lot of places, I found that people hand out these sparkies, all kinds of little gems, nano gems, diamonds, and kids are very happy. But that happiness is transitory. I think it lasts for about a month or 2 months, in which time they do learn a lot. Just by enticed by the reward, they learn a lot in those 1 or 2 months. But after that, the charm wears away, and I think they don't follow on that. So it's not a continuous reinforcement, it's a one-time reinforcement. These kinds of rewards are one time. They do not last. They are not deep, they are very shallow. But as a parent, I can say it does work. In the short term, it works. Get to know about different terms. Of course, they know about the terms because the terms are in the.
No, like if I will rotate, it will do something, the nature. But what that mean, like?
Are you talking about the language of science?
Yes.
So that was a conscious intent. In the first version, we didn't have the language of science embedded into the application. It used to only show the phenomena, and actually there was no guidance. In this version, actually there is guidance in the sense there are some, I didn't show you in the demo, there are some places where it actually explains, and it says this is what actually happened.
Okay.
So it tries to consciously build the language of science while talking, and maybe you noticed whenever you touch something, there's a status bar which keeps saying, you did this, you did this, you did this. The magnet got rotated. So hopefully that language is getting implicitly built into their heads.
Okay.
Okay, thank you very much. It's been a pleasure.
Thanks, Sridhar. Guys.